Hello everyone, welcome to the class on the material science. So today we'll be discussing about the imperfections in atomic and ionic arrangement. Just as a precaution and note here, because this is a video recorded one, all the contents for this slide, including the figures, are taken from the material science book by Askeland. So the objective of today's class is that by the end of this class, you guys should be able to understand different types of imperfections in atomic and ionic arrangement, as well as explain the impact of imperfections on material properties. So there are basically three basic types of imperfections known as point defects, line defects, which are also called as dislocations, and we have surface defects. These imperfections, they only represent the defects in or the deviation from the perfect or the ideal atomic or ionic arrangement in a given crystal structure. But that does not mean that material itself is considered defective from an application viewpoint. Actually, the defects are sometimes created intentionally to produce a desired set of electronic, magnetic, optical, or mechanical properties. So with that, let's get started with the point defects. Point defects are the localized disruptions in an otherwise perfect atomic or ionic arrangement in a crystal structure. Even though we call them point defects, the disruption actually affects a small region involving the several of the surrounding atoms and ions. These imperfections may be introduced by the movement of atoms or ions when they gain energy by let's say heating, maybe during the processing of the material or by the introduction of other atoms. So based on that, there are different types of point defects. So the first one shows the vacancy. This one is called as interstitial atom. This one is substitutional defect, small substitutional defect, large substitutional defect. Then we have Frankel defect and Schottky defect. So all of these defects, they disrupt the perfect arrangement of the surrounding atoms and create strain in the crystal structure. As you can see, all of these defects have some form of dislocation or distortion in this crystal structure. So before going into more details about the point defects or other types of defects, there are few terminologies that you need to understand. First one is impurity. So the impurities are actually the elements or the compounds that are present from raw material or from processing. For example, the silicon single crystal structures that are grown in quartz crucibles, they often contain oxygen as an impurity. And then there are dopants, which are actually the elements or the compounds that are deliberately added in known or calculated concentration at a specific location in the microstructure with an intent to get beneficial effect on the properties or processing. So the effect of impurity is deleterious or it is harmful to the material of concern. While the effect of dopant is useful, it is actually used to enhance the properties. For example, the phosphorus and borons are examples of dopants that are added to the silicon crystals to improve or alter the electrical properties of pure silicon. Let's go and look into different types of point defects, starting with the vacancies. So you can see there is a vacant space, there is a missing atom in the crystal structure. So vacancy is produced when an atom or ion is missing from its normal site in a crystal structure. So when these atoms or ions are missing, or in a way saying when the vacancies are present, the randomness or the entropy of material increases, which actually increases the thermodynamic stability of a crystalline material. And that is why all these crystalline materials, they have a vacancy defects. The other defect is interstitial defect. So you can see the extra unwanted atom in the regions which is not in the crystal structure. So this type of interstitial defect is formed when an extra atom or an ion is inserted in crystal structure at a normally unoccupied position. For example, these spacing between the atoms, they are normally unoccupied by any kind of atoms or ions. But when you get undesired atom or ion here, then that is kind of interstitial defect. So they are usually much smaller than the atoms of the actual crystal structure, but they are large enough to cause the distortion. So you can see the spacing between these four atoms versus these four, that is different. So they cause some sort of distortions to the overall crystal structure. So the interstitial atoms such as hydrogen are often present and as impurities, but then there are other interstitial atoms such as carbon atoms that are intentionally added to iron to produce steel. Steel is stronger and harder than iron, so they are both impurities and dopants. So you can see that so carbon atoms occupy interstitial sites in the iron crystal structure that they introduce a stress in the localized region of this crystal in the vicinity. So if the if there are dislocations in the crystal that are trying to move around these type of defects, they face resistance because of these interstitial atoms, and then it um, makes the permanent deformation in metals and alloys even harder. That is why we add these kind of interstitial defects in material processing to get harder materials. This is one important way of increasing strength of metallic materials, and usually interstitial defects are introduced in metallic materials. So, so unlike vacancies, once the interstitial defects are introduced in the crystal structure, the number of interstitial atoms or ions in the structure, they remain usually constant even when the temperature is changed. But vacancies, the number of vacancies that change as the temperature of material is changed. The substitutional defect is when the atom is substituted by another atom. It can be smaller than the original atom or it can be bigger than the original atom. So this defect is introduced when one atom or ion is replaced by a different type of atom or ion. The substitutional atoms or ions, they occupy the normal lattice sites as opposed to the interstitial, where it occupies the spacing between the atoms, or vacancy when there is um, no atom in the crystal structure. So these kind of defects, they alter the interatomic distances in the surrounding crystal. So here the interatomic spacing is decreased in this case. However, it is increased in this case. So the substitutional defects, they can be introduced either as impurity or as a deliberate alloying addition, such similar to interstitial defects. Some examples include the incorporation of dopants such as phosphorus and boron in silicon. The substitutional atoms will often increase the strength of metallic material, similar to interstitial defects. The other two important types of point defects are Frankel defect and Schottky defect. Frankel defect, you see that one of the molecular ion goes to another interstitial position, causing a vacancy in here. While in Schottky defect, we have a pair of positive and negative ion missing from each other. Here we have a positive ion missing, and here we have a negative ion missing. So the Frankel defect is a vacancy interstitial pair formed when an ion jumps from normal lattice point to interstitial site, leaving behind a vacancy. So here we have vacancy, where we have interstitial pair. That is why we call Frankel defect as vacancy interstitial pair. Usually the Frankel defect is described for ionic material, but it can occur in metals as well as covalently bonded materials. Schottky defect is unique to ionic materials only and is commonly found in some ceramic materials too. In this defect, the vacancies occur in ionically bonded material. So what happens here is the stoichiometric number of anion and cation is always balanced if the electrical neutrality is to be preserved in the crystal. What that means is, for example, if we have a magnesium plus plus ion and oxygen minus minus ion missing in magnesium oxide, they make a Schottky pair. But in zirconium oxide, for one missing zirconium ion, there will be two oxygen ions missing. So here, in this case, for one ion missing, here is for one positive ion missing, we have one negative ion missing. But if we are dealing with something like zirconium oxide, for one of those zirconium element missing, we'll have two of these positive or negative terminals missing. Yeah, so this class has a lot of new terminologies, and it might be overwhelming to understand and remember all those terminologies. So what we'll do is we'll watch this YouTube video. It's kind of a good analogy which relates this kind of defects we discussed in real life scenario. So we'll watch this video and we'll continue to the dislocations. So let's watch this video.
In a fruit stall, a set of fruits arranged in a finite order or a regular pattern resembles a crystal structure. If a consumer takes a fruit from the rack, a defect happens in the arrangement of the structure. The defect in the regular arrangement of atoms, which is assumed as fruits here, is known as crystal imperfections, and the defect occurred here is known as point defect. The shopkeeper was arranging the fruits in a hurry, and the particular column of fruits was misarranged, known as line defect. In a school function, seats are arranged in a regular order for each student and their parents, where the parents are considered as an IO and the student as cation. One of the student's parent and the student couldn't make their presence, and the place was vacant, which resembles the vacancy defect. If a student leaves his seat and goes to an interstitial space, then it is known as interstitial defect. And if someone else occupies the vacant seat of a student or the parent, it is said to be a purity defect. While walking on the streets, Mark stopped a while on an energy train. Every element will have a specific structure. After taking the energy train, you squeeze the dent and throw it away. When the stress gets applied on the dent, deformation occurs. As a partial force was given to the lattice, dislocation gets moved in the tin structure and causes the bonds to break. After throwing it away, the tin got squeezed. Assume a lattice box, and an amount of force is applied to both the sides of the box. When the force is applied to the lattice box, one atomic spacing has been shifted. In this case, dislocations move in large numbers with an amount of force equal to 10 in the middle of the forest, considered as dislocated crystal with x-axis and y-axis. When he was out in search of food, he decides to track his footsteps to get back to his tent. He takes 2 steps in the positive x direction and 4 steps in the positive y direction. Correspondingly, 4 steps in the negative x direction, 4 steps in the negative y direction, and 2 steps in the positive x direction. But, due to land dislocation, he couldn't reach his tent. So, he used a rope to climb down to the tent, where the rope is the Berger vector. Berger vector is a displacement vector, which finishes the closed loop-like structure when traversing an equal number of lattice steps around the defect.
So that was it. Let's continue from where we left. So I hope that gives some idea, and you can come back and watch this video again to get some good analogy on the types of defects. So the next topic is the dislocations. The dislocations are the line imperfections in an otherwise perfect crystal. So they are typically introduced into crystal during solidification of material or when the material is permanently deformed. So we'll talk about solidification on coming chapters of this course. So the although the dislocations are present in all materials, including ceramic and polymers, they are particularly useful in explaining the deformation and strengthening of metallic materials. So our focus will be on mostly on metallic materials. There are 3 different types of dislocations: screw dislocation, edge dislocation, and the mixed dislocation. Mixed dislocation is basically the combination of screw dislocation and the edge dislocation. Let's start with the definition of screw dislocation. So screw dislocation can be illustrated by cutting away through a perfect crystal and then screwing the crystal in one atom spacing. What does that mean is if we have this perfectly rectangular crystal structure, we cut this crystal structure somewhere up to halfway through the rectangle in the depth direction, and move this part half left half upward and then right half downwards. What that will cause is it will cause a dislocation, which is basically the initial plane remains the same height for both sides, but in the center where the dislocation happened, the crystal structures will move up by 1 and by down by 1, and the opposite side. So in doing that, if you start from point X and go in positive direction, and positive, let's say this is the positive X direction, this is the positive Y direction. So if you start from X, go to positive X direction by few number of atomic spacing, and then go to positive Y direction by this few number of atomic spacing, and come back on the X direction on the same atomic spacing you had been traveling, and then back to Y axis, negative Y axis. You end up one atomic spacing below the original point where it started. And there is a vector that connects this final travel point to the initial travel point, which is known as Burger's vector. So this is the similar description that we saw in the video I just explained. So if you start from one point and make one revolution, you end up in a point which is one atom spacing below the our starting point. And that vector required to complete the loop and return to our original point is known as Burger's vector B. And in case of screw dislocation, the Burger's vector is parallel to the screw dislocation. So this is the screw dislocation direction, and the Burger's vector is parallel to the screw dislocation. So edge dislocation is another dislocation, and it can be illustrated by slicing the perfect crystal. So this is the perfect crystal. If you slice into multiple parts and you insert extra half slice from the top, what does that is the bottom spacing remains same here, but the upper one is changed. And since we have this half slice here, the atomic structure in this case only ends up to this point, causing a edge dislocation in here. And if similarly, if we start traveling from a given point in X direction and then in Y direction and follow back on the same negative direction of the X and negative direction of Y, we end up in a location that is one atomic spacing below the starting point. And the vector required to connect this Y point to X point is again known as Burger's vector. However, the only difference is in this case, the Burger's vector is perpendicular to the edge dislocation as compared to the screw dislocation where Burger's vector was parallel to the dislocation. So this gives the same description that I mentioned and that you saw in the video. So the Burger's vector is perpendicular in edge dislocation and is parallel in the screw dislocation. That is something you have to remember. Mixed dislocation is basically a combination of the screw and edge dislocation with the transition in between them. In this case, though, both dislocation go through the same Burger's vector. So in this side, we see screw dislocation. And from here, if you look into this region, you see the edge dislocation. And this mixed dislocation can be explained with the help of what is called a slip line, slip plane, and slip or Burger's vector for both edge dislocation and for screw dislocation. So if this is the dislocation line, the slip plane is where the slip happens. Slip vector is the direction where slip happens. So for the edge dislocation, it is on this direction, and for the screw dislocation, the slip vector is on this direction. So basically parallel to the dislocation line for screw and perpendicular to the dislocation line for edge dislocation. That brings us to the definition of slip. Slip is the process by which a dislocation moves and causes a metallic material to deform. The direction in which the dislocation moves, or the slip direction, is the direction of Burger's vector for the edge dislocation. So during the slip, edge dislocation sweeps out the plane formed by Burger's vector and the dislocation. That plane is called a slip plane. So if you go back and look into a couple of slides, so this plane, where the slip vector goes from the dislocation line to the start of the force. Similarly for the screw dislocation, this is where the slip happens. So that is called as the slip plane. So the combination of that slip direction and slip plane is called a slip system. Screw dislocation produces the same result. The dislocation moves in the direction perpendicular to Burger's vector. That is only the difference, although the crystal deforms in the direction parallel to Burger's vector. Yeah, I know there are so many new terms and definitions here, but keep trying to remember those, and if you need to revisit those. So let's move to the significance of dislocations. Dislocations are most significant in metals and alloys because they provide a mechanism for plastic deformation, which is a cumulative effect of slip of numerous dislocations. So that brings us to definition of plastic deformation, which is the irreversible deformation or change in shape that occurs when force or stress that cause the deformation is removed. So that happens because the applied stress causes dislocation motion in that turn, and that turn causes the permanent deformation. While the elastic deformation is a temporary change in shape that occurs while a force or stress remains applied to material. In elastic deformation, the shape change is a result of stretching of interatomic bonds. However, there is no dislocation motion occurring in elastic deformation. Slip can occur in some ceramics and polymer material too. However, the other factors in ceramic and polymer, such as the porosity of ceramics and the disentanglement of the polymer chains, they dominate the mechanical behavior of polymers and ceramics. So they are not as significant for polymers and ceramic as they are for the metallic materials. Amorphous materials such as the silicate glass, they do not have periodic arrangement of ions and hence they do not contain any dislocations. Slip process is particularly important to understand the mechanical behavior of materials. Slip explains why the strength of metal is much lower than the value predicted from metallic bond. So metallic bond has high strength. However, when slip occurs, there only a small fraction of metallic bond energy is required to interfere and break the bonding. It's similar to crack. If you have a material that has surface cracks and if you try to break that material from that crack, you can easily break it. However, the overall strength of that material is higher. Slip also provides ductility in metals. So if there is no dislocations were present, an iron bar would be brittle and the metal would not be shaped by the metal working process. So slip in a way is a good thing because it provides ductility so we can do metal working process and change the shapes of different types of metals. And we control the mechanical properties of metal alloy by interfering with those movements of the dislocation. That brings to the definition of Schmidt's law. Schmidt's law describes how single crystals deform. So basically, if we apply a stress and we calculate the shear stress in the slip direction using the laws of trigonometry and the forces, Schmidt's law describes that tau r, which is the resolved shear stress, is given by sigma normal stress times cos phi and cos lambda. Cos phi is the angle between normal stress to the normal to the slip plane, and cos lambda is the angle between the normal stress to the slip direction. And if this tau r, which is the resolved shear stress, is greater than the critical resolved shear stress, which is a constant material property. If that is greater than the critical resolved stress, the material will slip and break. So this critical resolve shear stress is constant for given material, meaning that it does not change for that material. So now let's move to surface defects. Surface defects are the boundaries or planes that separate material into regions, and each region having the same crystal structure will have different orientation. So the material surface is different than the material core because the exterior dimensions of the material, they represent surfaces at which the crystals abruptly ends because we cut those surfaces and things like that. So each atom at this surface has no longer the proper coordination number and the atomic bonding is disrupted. This is an important factor in making devices, especially microelectronic devices, because the exterior surface may be very rough and may contain tiny notches, which may be much more reactive than the bulk of the material. So to demonstrate that, what does it mean is if you have a material with a crystalline structure that are irregularly spaced, they are separated by different boundaries here, which is basically the combination of irregular areas. So the atoms near the boundaries of these three grains, they do not have equilibrium spacing arrangement. You see that they have different atomic arrangement, but other part of these grain boundaries, they have regularized crystalline structures. And if you look into the grain boundaries using a microscope, this is an example of the stainless steel sample. These are the grain boundaries and the grains are inside the grain boundaries. So they look different, but they are all crystalline structures here. So if you look into microstructure of many of the engineered ceramics and metallic materials, they consist of many grains, which brings us to the definition of a grain. A grain is a crystalline portion of the material within which the arrangement of the atom is nearly identical. And going back to this example, the arrangement of atoms is nearly identical in this case, and this case. But then they are organized in different orientation in each cases. So the orientation of the atom arrangement or crystal structure is different from adjoining grains, and hence the grain boundary is the surface that separates the individual grains is a narrow zone in which atoms are not properly spaced. So one of the method of controlling the properties of materials is by controlling the grain size. By reducing the grain size, we increase the number of grains and hence the amount of the grain boundary area. So any dislocation that moves only a short distance before encountering grain boundary and being stops, and the strength of metallic material is increased. That their behavior is given by the equation called as Hall-Page equation, which relates the grain size to yield strength. So sigma y yield strength is given by sigma naught plus k d to the power minus 1 by 2, where sigma naught is initial strength constant per metal, and then k is another constant for material, and then d is the average diameter grain. So basically, with the decrease in the average diameter of grain, the sigma y increases. That is the Hall-Page equation. So to see the grain boundaries, optical microscopy is one technique which is used to reveal the microstructure features such as grain boundaries that require about 200 to 2000 times magnification. So we cannot see these microstructures of materials with our naked eye. So we need some techniques. So the process of preparing a metallic sample and observing or recording its microstructure is called metallography. In metallography, what happens is we have a sample of material that is sanded and then is polished to a mirror-like finish, so polished to a clean finish, and then that surface is exposed to chemical attack or etching. It's a method of chemically exposing the surface to optical microscope, with the grain boundaries being attacked more aggressively than the remainder of the grain. So if you have a smooth surface, the grain boundaries are aggressively attacked with these chemicals, and then the light from optical microscope is reflected or scattered from the sample surface, depending on how the surface is etched. And since more light is scattered from deeply etched features, such as the grain boundaries, these features appear dark in microscope. So this is an image of the microstructure of the palladium crystals. You see that the darker areas, they are the grain boundaries, and the lighter areas, they are the actual grains. So we discussed the different types of defects, but it's also important to understand why the defects are important for us for any kind of material processing, because we can control the strength of metallic material by controlling the number and type of imperfections, and also sometimes we can control the properties of other materials such as polymer or ceramic material by controlling those imperfections. There are three common strengthening mechanisms especially applied to metallic materials. One is strain hardening, the other one is solid solution strengthening, and the last one is grain size strengthening. So strain hardening is when a metal gets stronger and harder as it is permanently deformed. This deformation causes microscopic defects or dislocations in the material's crystal structure to get tangled and block each other, and making it harder for a material to deform further. So basically, you beat a piece of metal until there is no area for the dislocation. It makes the metal stronger. Solid solution hardening is another mechanism which is defined as a technique for enhancing the strength of pure metal. This is something you have to remember. Pure metal by alloying it with the elements that integrate into crystalline lattice. So basically adding a dopant that forms either a substitutional or an interstitial solution, which impairs the dislocation motion and makes the plastic deformation more difficult. The final one is called as Hall-Page strengthening or grain size strengthening. It is defined as the phenomenon where a reduction in the grain size leads to an increase in yield strength in material due to the higher density of grain boundaries acting as obstacle to the dislocations. This relation can be described by the Hall-Page equation that we discussed earlier, which links the grain size to the strength. So I think with that, I'll conclude today's lecture. I know there are a lot of information that needs to be remembered. I hope you'll rewatch this video and make sure you understand all those terms and remember all those terms. If you want to explore more, please go ahead and read the chapter 4 of the book, Askeland book. Final reminder that assignment 1 is out and is due on February 12th. With that, in the next class, we'll discuss the atom and ion movements in material, and next class will be in person in class. Thank you, everyone. I'll see you in class.